All right, our definition of a limit. The limit of f of x as x approaches c is L. So that's what how we would say this limit right here. So as we look at that, the way we would read that is the limit of f of x as x approaches c is equal to L. So if we look at one we looked at before, something like that, we would say that is the limit of 5x plus 1 as x approaches 3 and is equal to 16. Okay. So what does that mean? So today what we want to do is we want to look at a more formal definition of a limit. And we started yesterday and we kind of wrote it down. So we want to look at it. So what does this mean? This means f of x gets close to L as x gets close to c. What does that mean? Let's go back to that one here. So let's consider this. So if I used my calculator and I want a number close to 3, what is a number close to 3? Give me a number. 2. Okay? So if I take 5 times 2, was it? I don't even remember. Was it plus 1? I got to remember what I had. Yeah. Now, how close to 16 is 11? I mean, it's close compared to 100, but it's not, right? So we want to pick a number closer to 3. So how about 2.9? Now we're getting closer to 16. Or we could pick 3.1. That's close to 16. Could you come up with a number closer than 2.9? 2.99. Exactly. So what this is saying is as I pick numbers that are closer and closer to 3, this gets closer and closer to 16. That's the definition of what a limit means. Now, if I pick a number bigger than 3, that's going to get closer to 16. Make sense? That's our idea of what a limit is. Now, in this case, we can just plug the number in. So it's like, seems kind of silly because it's just plug in 3. Why do we have to do all of this? We can just plug 3 in and get 16. Not always the case, but for right now, we'll just say that makes it easy. Okay. So the question becomes, what does close to mean? Mathematically, how do we define being close to something? So what we want to do is we want to try to define what does it mean to get close to. Now, you remember yesterday we talked about how to find the distance between two things? So we said, well, close to, f of x gets close to L. We said, well, if we said f of x minus L, that's the distance between them, right? We subtract them. X gets close to C, that's the distance between those. Follow me from yesterday? Now, we want this to be close, which means we want these distances to be less than something. If I said I want x minus c to be less than 0.1, that would mean I would have a number like 3.01. Because if I subtract that from 3, I get less than just 0.1, right? So I could put that number in, 3.01 plus 1, and then that number is that close to 16. Okay? But could we get closer? Yeah. So how do we define that mathematically? What does it mean to get close to? And to help us with that, we are going to use our formal definition of a limit. And this is where we ended up yesterday. So our formal definition of a limit is, if we have the limit of x as x approaches c, the same idea. If this is true, for every epsilon greater than 0, there exists a delta greater than 0, such that if x absolute value of x minus c is less than delta, then the absolute value of f of x minus L is less than epsilon. What does that mean? Let's unpack that a little bit. So first off, this epsilon and delta represent small numbers. Those are Greek letters. If you look at the Greek letters in the back of the board, those are lowercase. If you remember, we talked about yesterday, triangle is a capital delta. That means the change in something. This is the lowercase delta. Same thing. So epsilon and delta. So these are two mathematical things that we use to represent small numbers. Okay? Now, before we break down this definition, I want to show you another definition. We're going to just do some crazy math stuff here, so let's just have some fun with this. I'm going to take this part right here, and I'm going to rewrite that down here. Those two things say the exact same thing. So let's break it down. So as we go through here, so some of these symbols are on the back wall. Upside down A, if you look in the back, that is a math symbol for all. For all epsilon greater than 0, the backward E, that is a math symbol back there for there exists. So for all epsilon greater than 0, there exists a delta greater than 0. ST, also back there, that stands for such that. For all epsilon greater than 0, there exists a delta greater than 0, such that if absolute. Can you see how this and the one above are the exact same thing? But instead of using words like for every, we use all of these math symbols. These are basically words that we use so often in math. We have a symbol for them, so we don't actually have to write out all the words. So as we continue to use this, we will read it, I'll say it out loud, but some people like the bottom one because it looks cooler with all the math symbols in there, right? It looks like some made up language kind of thing, okay? So what does this mean? So let's break down what this means. For every epsilon, there exists a delta. So what this means is you pick here, epsilon. How close do you want to get? And then you want to get that close, then I can pick a delta that will get you that close. And let me give you an analogy. Let's say I want to walk from here to Jack's. And I want to say, how close do you want to get to him? And let's say I want to get within 10 feet. So if you say, okay, I want you within 10 feet, I can say, well, if I take 2 steps, that gets me within 10 feet. And then you're like, you know what? 10 feet's not close. I want you to be within 5 feet. Well, in order for me to be within 5 feet, what am I going to have to do? I'm going to take maybe 4 steps. And then that will tell me how close I want to get. And you're like, well, 5 feet isn't close. I want you to get within 1 foot. And I'm like, well, to get in 1 foot, it's going to take me 7 steps. So the idea here is you can get as close as you want. You tell me how close you want me to get, and I will get you that close. That's the idea of what this theorem is. So let's do an example. I'm going to grab the notes here so I have the same thing here. That's the wrong one. All right, so let's go. All right, we're here. So I'm going to grab a calculator. So we can do this with a calculator. So let's look. So we must first pick an epsilon. So let's pick an epsilon as 0.1. Okay. So here's our limit. The limit of 3x plus 5 as x approaches 2 is equal to 11. And we're going to unpack this, so just kind of stay with me, and hopefully as we go further, it'll make more sense. So just follow along. So we want our epsilon to be 0.1. So that means, from our definition, that f of x minus L is less than epsilon, which tells us that 3x plus 5 minus 11 is less than 0.1. Now I'm just going to do this one first, and then as we go through, I'll kind of tell you how you know what to do, but let me show you what I'm going to do here. So I am going to say this then becomes 3x minus 6. I'm going to factor out the 3. Like I said, stay with me here and I'll show you why we did this. Now, once we have that 3, one of the properties of absolute value is if I had 3 times that, technically this is equal to the absolute value like that. Okay. You can, if 2 things multiplied together are in absolute value, they have to be positive, right? So if I take the absolute value of each part, they both have to be positive, so when you multiply them, it still works. So absolute value of 3 is just 3. So what we end up with is x minus 2 is equal to that. Now, what have we just done? Okay, what have we just done? So we started here. Notice here, x is approaching 2. So in our definition of a limit, we have x minus c. We're always going to end up with, down here, x minus c. So that tells you where you're going. You're always going to start at f of x minus L, and you're going to end up with, down here, minus c. So that tells you know where we're going. So what have we done? All right. So what we have found down here is our delta. Okay, just trying to get you to understand what we're talking about here. So let's look at this. So our delta is 0.1 divided by 3. 0.1 divided by 3, which is 0.033333. So let's consider, I'm going to write it this way. Let's consider here is 2, and I want all the numbers that are this close. I didn't give you a lot of space there, but all the numbers that are this close. So if I take 2 plus 2.03333, and then I do minus 1.96667. So these are all the numbers that are that close to 2, right? All of these numbers are that close to 2. Does that kind of make sense? I'm adding and subtracting the delta. Now, if we consider f of x, and we said f of x is equal to 11, and I take 3 times I get 11.1. $10.9. All right, so let's see if we can understand big picture. We did a whole bunch of calculations just to understand. We're not going to actually do this a lot. I'm just trying to get you to understand what's going on. So if you pick any x in here, those are all the x's that are that close to 2, right? If you pick any x that's in here, whatever that number is right there, I don't know what it is, but it's a little less than 2. Whatever that number is, if you plug that into our equation, the functional value would be about right here, and that would be in 0.1 of 11. So if you pick an x this close to 2, your answer will be within 0.1 of 11. Does that kind of make sense? If you want to be that close, X's in here will get you that close to 11. You want to get within 1 foot of Jack's, you got to take 8 steps. So 8 steps will get you that close. Now, Grace's like, yeah, 0.1's not close. It's on your nose. I don't have it up here. What if we want to be within 0.001? You want to be even closer. What we could do is we could do the whole thing over again with 0.001. But if you go back and look, if I change this right here to 001, what would change? This would become 001, 001, 001, 001, 001. That's all that would change, right? Now, this number would be different, and this would change. And what would happen? This number would get smaller, wouldn't it? It would be 0.001 divided by 3, which is 0.00003. So think about what would happen down here. Wouldn't this number be smaller? So I'd have a smaller area around 2 that would get me to a smaller area around 11. So what we're going to do is that number doesn't really matter. So we're just going to do these by saying just epsilon. And find, for any epsilon, find delta. Okay? So now we are ready to do this. So first one here I'm going to work through is not on the back, is kind of still on the front, but watch it. So this is how we're going to actually solve what these problems were. All that we just kind of went over was trying to get you to understand what we're doing, kind of big picture a little bit. Okay? So here's what we're going to do. We're always going to start with our f of x minus L is less than epsilon. So that is going to be 3x plus 5 minus 11 is epsilon. Now, we know we have our number right there is 2. So what we're going to do is we're going to try to end up down here at x minus 2. So in all of these, you're going to start here and trying to do algebra to end up there. So you know where you're ending. You know what you're trying to get to. You know what you're trying to make it equal to. So, and it's always going to kind of work out this way. We're going to 3x minus 6. We have a 3 in there, so we can factor the 3 out to get to x minus 2. And then we can divide by 3. So we get to epsilon over 3. So for any epsilon, let epsilon, our delta, is epsilon over 3. So let's go back to our definition here real quick. If we look at our definition here. Our definition says for every or for any epsilon. So you say for an epsilon. Now we're just going to use epsilon as a variable. It could be 0.1, it could be 0.1, it could be 0.0000001. We're going to say for some epsilon, there exists a delta. We want to find that delta. We found that delta to be epsilon over 3. Whatever your epsilon is, your delta then is epsilon over 3. Here, if we say it was 0.1 or 0.001, we had a number. Now we're just going to say it's over 3. Okay. So let's do a couple of these before we kind of go to the next step. So let's say we have the limit 2x plus 4 as x equals -1 is equal to 2. Okay. The first step is always f of x minus L is less than epsilon. So we'll take this step. So first, fill in what is your f of x and what is your L there. So this should be 2x plus 4 minus 2. The next part you want to think about, what are we trying to get to? As we move down here, what are we trying to get x down here? And it's x minus our c, which in this case is -1. So we're trying to get to x minus a -1, which is a +1. So we are trying to do our algebra to get from here to there. Try that, see if you can figure that out. How do you combine like terms, factor stuff out to get from 2x plus 4 minus 2 down to x plus 1? Combine like terms. We're trying to get that here so you can see factor out of 2. Finally, we're going to divide by the 2 to get to there. So for any epsilon, find delta. Our delta is epsilon over 2. Okay. All right, try another one. For the limit of x squared plus 5 as x approaches 0 is equal to 5. Same thing. What do we want to get to at the bottom? X minus 0. Now, I know you don't really need a minus 0 there, but it kind of fits the same pattern that we've been looking at. So you go through that, okay? So go ahead, plug in your f of x and your L and see what happens. So what do you get? Exactly, because you have minus 5, right? So you get x squared is less than epsilon. So to get just x, can you do that? Can you just take the square root of an absolute value? What's absolute value do? Makes it positive. So just think about that practically. If you have x squared here, would that be the same thing as that? We're not dealing with anything with imaginary numbers or i's. We're only using real numbers. So if you square any number, it's going to be what? positive, so you don't really even need the absolute value, right? Because it's going to be positive. And if you take the absolute value of anything and it's positive and you square it, it's all still the same thing. So yes, we can take the square root of that, and it works out. And so we get our delta is equal to the square root of epsilon. All right, so another one. The limit of 7 minus 3x as x approaches 4 is equal to negative 5. Do the same thing. Think about what we want to get to. Try that one. Both of you wrote it 12 minus 3x, right? I switched the order like this to put the x first just because of where we're going. So we want to get to x minus 4. So what do I have to factor out?
Negative.
Negative 3. So I have negative 3 x minus 4. This is what happens when you have a negative 3 inside an absolute value. A negative just becomes positive. So we just still divide by 3. The negative just becomes a positive. So one of the things that you may remember, if you flip your notes over, look back at the definition of a limit from the other side. If you look at the formal definition of a limit on the other side, how does it start out? For every epsilon, what?
Greater than
0. There exists a delta that is greater than 0. So you can't have a negative in your delta. So even though you have a negative 3 here, because it's in the absolute value, when you pull that out, you only get a 3. Okay? Your delta could never be negative. All right. Now, we just want to look at some other ones, some different things we can have happen. So I got another one. The limit of x squared minus 9 over x minus 3 equals 6. Now, first off, notice the limit's getting a little harder. Can you just take 3 and substitute it in? If you just substitute in 3, you get 0 over 0. Do we see that? So 0 over 0 equals 6. How do we get that? Today we're not worrying about that. That's the answer. We'll talk about why that is later. But let's do our rules. So what do we have? We have f of x minus L is less than epsilon. And what are we trying to get to down at the bottom? X minus 3 from our C. Okay. So let's put this in. We have x squared minus 9 over x minus 3 minus 6. Now, how would you do that? What's your first thought? There's two ways to do this one. So I'm curious if you have any thoughts or ideas on what you would do or anything jumps out at you with this.
Take the difference in squares and cancel out the exponents.
Okay, so your first thought was x squared minus 9. I can rewrite that as x minus 3, x plus 3. Right? Then that cancels, and I'm left with x plus 3 minus 6. And what happens when I simplify?
Yeah, X minus.
So we're there. So delta just equals epsilon. Okay. I'm not even going to go into it because you guys don't want to do it, but you could have, some people look at this and their first thought, don't even write this down because I would have tried to stop you and redirect you if you would have thought this way. Some people think, do something like that and get common denominators and then combine them into a fraction. Does that kind of, if you did that, it ends up factoring and canceling and you end up in the same place. But that's more work. Your idea that I was going to try to, if you went the other way, I was going to try to get you back to this way because this way is easier. Okay. All right. Let's look at, I'm going to skip some of these because of time. Look at this one. Let's look at the limit of 1 over x plus 1 as x approaches 2 is 1/3. So let's just kind of work our way through this one. We have f of x minus L is less than epsilon. And what are we trying to get to?
X minus 2.
X minus 2. So here we are going to need common denominators. So I'm going to multiply by 3 over 3 over here, x plus 1 over x plus 1 over here. So this will give me 3 times x plus 1 all over 3x plus 1, like that. Now if I simplify the top, this gives me minus x plus 2. Think about where we're trying to get to. So on the top, I get to there. So far, so let me pause there. Have we followed what we've done so far? Okay. Now, what can you do with a negative inside an absolute value? Just make it positive? And what is a negative 1 inside an absolute value? We could just be like, let's just get rid of that. Now the question is, what can we do now? Now we got to go back to the top and think about this. What is x getting close to? 2. So let's consider the bottom. As x gets close to 2, this gets close to what?
3. Oh, wait.
3, and then times 3, or 9. So as x gets really close to 2, this kind of gets close to 9, right? Follow me? Now, we want to find this over here. So if we just multiply by 9, we don't know. This could be 2. Couldn't a number close to 2 be 2.1? And if it was 2.1, wouldn't 2.1 be bigger than 9? Do we follow that if I put 2.1 in there? 2.1 plus 1 would be 3.1 times 3 would be like, it'd be 9.3, right? Does that make sense? It'd be bigger. So because of that, we don't want to just use exactly 9 because the number close to 2 may be a little bit bigger than 2. So when we do this and we say this is close to 9, when we add the number here, we're going to add 1 and say 10. Because this number may be a little bit bigger, maybe a little bit smaller than 9, so we'll just go bigger. And so if we have a number that's a little bit more than 2, it's not going to be a lot more than 2 because it's approaching 2, but that would allow us to get to there. Okay. All right, we're going to stop there for today. Let's look at homework. Let's skip on the homework 4 and 5. So if you look on the back, we can do 1, 2, 3, and 6. I'm going to skip 4 and 5. We kind of ran out of time. I will come back. We'll talk about those next week. I'm not sure if I'll give them to you for homework or we'll just kind of do them in class next week. So you have the back, the 4 problems on the back, and 4 problems on the front for homework.